Hello everyone, my name is Gongxuan Yu from Okayama University. Today, I have very pleasure to present our work. Study static pressure fluctuation amplification by engineer conservation uncertainty in areas of isotropic steady turbulence. Incompressible turbulent flow are commonly found in industry and automotive application, and the computational flow dynamics solver such as OpenFOAM have been widely used to analyze them. Previous study using spectral and high accuracy discretization measures has focused on improving kinetic engineer conservation in turbulent simulations. While OpenFOAM has been validated for fundamental flow analysis, questions remain regarding its ability to maintain physical conservation laws with sufficient accuracy. In particularly, the relationship between turbulent kinetic engineer and the RMS of static pressure fluctuation has been discussed. Through experimental data remain limited. Therefore, large AD simulations are often used to analyze large-scale turbine structure with high universality. Although kinetic engineer conservation has been recognized as external for accuracy turbine analysis. Common CFD slower may not ensure sufficient conservation accuracy. This study aims to certify how such uncertainty in engineer conservation affects steady turbines characteristics using isotropic steady turbines sustained by linear forcing. The Cranison impacted time integration measure is applied to control conservation uncertainty. Large dissemination with the smuggling and coherent structure models are employed to examine the influence of large-scale turbine structure on turbine kinetic engineer and RMI study pressure fluctuation. By varying the forcing parameters, this study evaluates the effects of large-scale dynamics on turbine and quality, the impact of engineer conservation uncertainty. The flow analysis in this study is incompressible in the potential domain of periodic box. Here, one side of this periodic box domain is 2π. The governing equation are the continuity and Navier-Stokes equation for incompressible flow, one way to generate steady turbulence using the external force field of the governing equation in the linear forcing measure. In this study, the external force term is used in the governing equation to maintain the steady turbulence using the forcing scheme. The external force term F is given as F equals CUF, where C is the constant, UF is the velocity vector. The competence of the velocity vector UF, which constitute the external force term, are given as the previous study. The integral constant m contained in this velocity vector provides a characterization of the nature of the external force field. The number of spectral grade points was set to 62. For the Linus number, the baseline condition will set to 300, 600, and 900. For m equal 1, 2, and 3. Under this condition, the value of the model constants will optimized and the time series state or output as described below. The Linus number range was 500, 10, 1000, and 50, 100, 500, 1500 for m equal 1, 2, and 3. Both scaling equations are specially discretized using a fourth-order century difference scheme. Kinetic engineer conservation uncertainty were introduced while the implicated Craig-Nixon time integration to compare cases without such errors. We use the expected second order at space force measure and the fourth order longitudinal measure for validation. The position equation is solved directly using the FFT. The dependence of turbulent kinetic engineer on model constants will analysis for each external force using both the coherent structure and smuggling model. a smuggling scheme model. Figure 1a-C show the coherent structure results, and Figure 1d-F show the smuggling scheme result, with CSS and CS as the respective constants. For m equal 1, connected engineer reaches about 5 and decrease as the constants increase. The smuggling scheme model is slightly more sensitive. For m equal 2 and 3, engineer is lower but shows the same decreasing trend. DNS results from the spectral measure were used for comparison, and fix helped identify the optimal model constants for each case. Figure 2a compares the optimized model constants value at each external force of the coherent structure model with the reference model constants value. Figure 2b compares the squared value of the model constants obtained by optimizing the smuggling scheme model value for each external force with the squared value of the reference model constants value. For both model constants, the value of the model constants at m equal 1 are the largest, and the difference in the value of the model constants between 2 and 3 is small. The optimized value obtained for the model constants are also compared to their reference value in the figure. In all results, the optimized value of the model constants are lower than the reference values. In this study, structure functions were used to assess how different m value affects turbulence structure. Second and third order structure function in the x direction will evaluated. For m equal 1, the second order function grows with distance. For m equal 2, it peaks around r over pi equal 1 over 2, and decreases at larger distance. For m equals 3, the second order function has the max near r over pi equal 0.33 and the minimum near r over pi equal 0.66. The two AGS models show quantitatively similar second order distribution. Three order function matched at small distance but differ at larger ones. These results indicate that large-scale turbulence structure were with A. Numerical visualization is used to show differences in large-scale turbulence structure. Figure 4 shows the isotropic of the negative instantaneous pressure fluctuation, with the P equal -3 for m equal 1, and P equal -1 for m equal 2 and 3, based on mean turbulent connecting engineer difference. For m equal 1, large structure turbulence structure are observed. Similar in both the coherent structure and the smuggling scheme model. For m equal 2 and 3, the structure visualized by negative pressure fluctuation are finer. And this is consistent across both AGS model. The study shows the optimal AGS model constants differ significantly among m equal 1 to 3. The figures suggest that this difference in optimal value are related to the large-scale turbulence structure, highlighting how varying m affects turbulence pattern. This study examines fluctuation of starting pressure. Figure 5 presents the time series of the spectral RMS of static pressure variation for 6 conditions at Reynolds number 300. Over non-dimensional time 300, 600 for all external forcing conditions, the spectral RMS varies significantly with time, both with and without connecting engineer conservation errors. For m equal 1, the RMS fluctuation around 2.5 when conservation uncertainty is negligible, but increased to about 3.5 when uncertainty is present. Similar increase occur for m equal to 3, These results indicate that conservation uncertainty evaluates the spatial variation RMS of static pressure. Demonstrating that connecting engineer conservation error enhance pressure fluctuation magnitudes, independent of difference in large-scale turbine structure. This study investigates the Reynolds number depend of the effects of kinetic engineer conservation uncertainty on the spectrometer RMS of fluctuation static pressure. Figure 7AC shows that conservation uncertainty increased the RMS for all forcing condition. Similar to the results at Reynolds number 300, the increase is comparable for M equal to 3. Although different M value produce different large-scale turbine structure, the increase in pressure RMS is less affected by this difference. Figure 7DF showed that the conservation uncertainty had little effect on the mean turbine kinetic engineer for M equal 1. Consistent with previous results, this insensitivity is also observed for M equal to 3. Despite differing M value, the Reynolds number distribution of turbines kinetic engineer remain constant with or without conservation uncertainty. That's all. Thank you for your listening.